Okay, in this note, okay, I just like to show you how from the Navier-Stokes equation, we could have a Bernoulli equation. So what is the difference between Bernoulli equation and the Navier-Stokes equation? So the Navier-Stokes equation is actually some kind of Bernoulli equation. So if the fluid move with certain velocity, so we could analyze them using Navier-Stokes equation. But if the fluid is incompressible, so we could use Bernoulli equation. So means the main difference between the Navier-Stokes and the Bernoulli is the Navier-Stokes equation can be used, normally people will use in compressible fluid, because the incompressible fluid, so the changes maybe goes to density, or it split into two portions. The density changes and also the velocity also changes. So, but in Bernoulli equation, the density is fixed all the time. So then here in this notes, I would like to show you how from the Navier-Stokes equation, people derive, and then we could get the Bernoulli equation. And normally, there are a few methods to get the Bernoulli equation. And normally in our undergraduate, we derive Bernoulli equation from the idea of energy. We start with the potential energy, we have kinetic energy, and then we have the pressure. Okay, but now I would like to show you how the Navier-Stokes equation can be used to derive the Bernoulli equation. So here it's like the weaker form. So the weaker form means we neglect, we have a few assumptions, and we neglect the changes of density. Okay, the Navier-Stokes equation can be written as this one. So this is the common Navier-Stokes equation. So in this here, because we assume that it is incompressible. So, and then we assume that there are no resistance. So the resistance means the viscosity effect. So we make assumption the mu is equal to 0. So actually in reality, the mu cannot be 0, because if the mu is 0, so means there are no molecule. Because mu is actually related to the shear stress. We know it's tau is equal mu du dy, so mean the mu is equal to the tau. Okay, so and then means that mu means shear stress. But in this calculation, we assume the fluid is ideal. So the ideal fluid, there are no resistance. So from where the resistance comes in, I think you already know the velocity distribution inside a pipe. There is one place where we call the no slip condition. So the no slip condition is actually the no slip condition where the shear stress is very high, so the molecule could stick on the surface very hard. So means that is the ideal. That is the resistance comes from. So but for Navier-Stokes equation here, so we are dealing with the ideal fluid. So means there are no resistance. That's why we could assume that the mu is equal to 0. So and then the mu here we could neglect the value of this one. So the Navier-Stokes equation now can be written as this one. So and then the Euler equation, from the Navier-Stokes there. So we could, because we don't have the mu, so we call it the Euler equation. So it can be written like this one. And then we divide by density, so we have this one. And then we could put a dot product with the displacement ds along the streamline, where ds is dx plus dy plus dz. This is actually the idea of the Euler. So and then we could rewrite it as this one. Okay, so this is just to get another things as shown in the next slide. Okay, so we have a lot of terms here. So we have this term, so and then we have this term, and we have this term. So we solve it one by one in this slide. So let's say we have negative nabla P over rho ds. So we put the ds here, mean the elongation or the distance of the, it's actually the dx plus dy plus dz. So and then we could summarize it as this one. So and then for the second terms, so we have this one, and then I think you could understand here. So because there are no gravity for x and y direction, so the only direction that effectively act with gravity, so is the dz, the vertical direction. So and then we have the third terms here. So I think you know in a previous tutorial we learned about how to simplify this one. Okay, v times nabla and v. So we have the dx plus dy plus dz. So and then it is okay just for your information. So finally this term will change into this one. And then so this is just to the idea of the nabla actually. So we have 1 over 2 nabla v square. So we could rearrange it, and then we could find that the value of 1 over 2 nabla v square can be written as this one. Okay. So and then the meaning of nabla is here, as in chapter 1 we described about this. So and then we substitute all the terms in Euler equation. So from this one, and then we could guess this one. And then you know that when we have the differential terms, we have dp, we have dv, and we have dz. We need to eliminate the differential form. So we do the integration. So if we do the integration here, so we will get here p over rho, and we have the integral here will cancel the d, the common idea. Okay, so and then we have p over rho v square over 2, and we have gz here. So and then if after we do the integration, so we could get the constant. So this is the Bernoulli equation. So normally in textbook they will write as p over rho g, p over rho g plus v square over 2g plus z. So this is the common Bernoulli equation, and the constant here actually the energy. So we know that conservation of energy is some kind of the momentum conservation. So means from the Navier-Stokes equation, actually we could derive to the Bernoulli equation that normally used in incompressible fluid. But for compressible fluid, please do not use Bernoulli equation. Okay, so and then the units for Bernoulli equation is meter. If you could see here, the z here is actually the height. So we use meter here. So what is the relationship between meter and energy? So this is actually the energy head. So means that it reflect for certain amount of energy. For example, you have 5 meter energy. What it is mean? So it is means that energy could leave that certain liquid up to 5 meter above the datum. So this is the meaning. So it's depend. If you use the rho here is the density of water, so means that 5 meter energy means that energy could leave water until 5 meter above the datum. So if you are using mercury, so mean that energy is the energy that could leave mercury 5 meters above the datum. So this is the idea. That's why the units for the energy is equal to meter here. So this is actually the notes, how people convert the Navier-Stokes equation to the Bernoulli equation.